In this poster, we are presenting a machine learning model which can accurately predict effective conductivities in copper-carbon nanotube composites with accuracy of more than 93%. Copper is widely used in many construction, transportation, and electrical applications due to its high electrical and thermal conductivity. As the things are getting scaled down, we need better alternates to copper to maintain device functionality at high currents and temperatures. Single-wall carbon nanotubes or CNTs are approximately 100 times more electrically conductive and 10 times more thermally conductive than copper. Therefore, researchers are very interested in fabricating copper CNT composites, which are theoretically proven to be superior electrical and thermal conductors than copper. When it comes to modeling such systems, several studies have reported different modeling techniques such as atomistic simulations, numerical simulations, closed form models, etc. These techniques not only require extensive computational resources but are very restricted in parameter space. However, if we combine machine learning and numerical simulations, we can explore large parameter space at relatively less costs than other techniques once the machine learning model is fully trained. So our objective is to develop a finite element model or FEM to calculate effective conductivities in stochastic copper CNT networks at various copper CNT interface resistances. Then we develop a machine learning model to approximate these effective conductivities without iteratively solving any governing physical equation. In FEM, we first generate stochastic 2D copper CNT networks with straight CNTs aligned to field direction. This reduces the computational load, enabling us to use high CNT volume fractions up to 80%. Then we apply the boundary conditions. We also apply CNT-CNT interface resistance for CNTs which are separated by a distance less than van der Waals spacing. FEM simulations solve the physical equations to get current and temperature distributions, which are then quantified into electrical and thermal conductivities. We also compared our work with previous to estimate what are typical interface resistances in bulk scale composites. After generating examples with FEM for machine learning, we perform simple data augmentation technique to quadruple our training data. Then we use a well-known machine learning algorithm called convolutional neural networks or CNN. A CNN model takes in an input image, assign learnable weights and biases to various aspects in the image, and be able to differentiate one image from the other. In our CNN model, we input the graphical images of copper CNT networks with the conductivity responses. CNN extracts and downsamples the information in each image using number of neurons and create feature maps. All feature maps are then connected and one-dimensional feature vector is created to establish the regression model for effective conductivities. The various hyperparameters of CNN are tuned and are listed in table. Here, we are showing a good agreement between our CNN model predictions and FEM calculations at different interface resistances. The validation accuracy for electrical and thermal conductivity predictions for the cases shown here is more than 95%. We can look at conductivity distributions in these plots to infer the effect of CNT fractions and interface resistances on electrical and thermal transport. When interface resistance is poorly regulated, both current and heat prefers to flow through copper medium, which is least resistive. So if we increase CNT fractions, the conductivities are reduced. The interface resistance is highly regulated. Current and heat prefers to flow across CNT networks, which augment the conductivities. So if CNT fraction is increased, conductivities are enhanced as well. The average simulation time per copper CNT network is around 155 minutes, whereas CNN model average training time is around 3 minutes for all 480 examples. Once trained, CNN model can approximate copper CNT network conductivities in less than 1 second. To conclude, in this work, we have utilized numerical simulations to generate training data for training CNN model. Once CNN model is fully trained, it can make rapid quantitative approximations of conductivities just by looking at image of copper CNT network without solving any two-ending equations. The possible extension of our work would be to apply a machine learning model on actual copper CNT networks. We would like to acknowledge our sponsors who made this work possible. Thank you for listening.